So if you recall the model and the estimated line, econometric model, so if you look at the econometric model and you have estimated that model using OLS formulas,
Professor,
yes.
could you give a summary, a review summary of what you did before this lecture? Because we had exams, then we did not have class last Sunday, so we don't
Okay,
remember
okay.
much.
So in that case, let's go back to the other slide which we did. New slide. Quickly going over the other slide. Can you see the other slide here?
Yes.
Econometric model and all this?
Yeah, a doc.
Huh?
Microsoft Word document.
Yeah. So basically what we wanted to do is we wanted to estimate the slope and intercept of economic relationship. So the econometric model where y is a function of x and it's a linear model here, y equals beta 1 plus beta 2 xi plus ui. So econometric model, and we know that the relationship is basically mean of y and x. So it's a linear relationship, mean of between expected value of y and x. The relationship is a straight line relationship. The intercept is beta 1 and the slope of that straight line is beta 2. However, the issue is we don't know beta 1, we don't know beta 2. These are called population parameters. We want to estimate them. There are many ways to estimate them. One way is to estimate them by minimizing residual sum of squares. So what is the residual? Obviously, residual is the difference between actual y and the estimated y. Estimated y you get from your estimated line, which we call y hat equals beta 1 hat and plus beta 2 hat xi. So these beta 1 hat and beta 2 hat are the intercepts and slopes respectively of your line, estimated line. This is the population line, actual line, but we did not see that. We saw there we are trying to find this estimated line. Now what is the principle to find this line? The simple principle is called least squares principle. What are you minimizing here? You are minimizing residual sum of squares. Residual is y minus y hat, actual y minus estimated y. And then if you have sample size 30, you have sample 30 ui hat, you square all of them, add them. Here you are squaring all residuals, I goes from 1 to 30 and add all of them. So you choose beta 1 hat and beta 2 hat so that this thing, the deviation square summation is minimum. So that is the principle. That principle you used calculus, choice variables here, beta 1 hat and beta 2 hat. You differentiated residual sum of squares with respect to beta 1 hat, beta 2 hat to end up with these two equations, normal equations of OLS. And from those two equations, simultaneously solving these two equations, you find beta 1 hat and beta 2 hat. You will see that everything here is known from data. So users take a sample, use these formulas to find beta 1 and beta 2. We did that in an Excel file. We actually calculated beta 1 hat and beta 2 hat. I also let you do the calculation in the midterm, beta 1 hat and beta 2 hat. And you get this estimated line from this estimated line. You can draw the line, you can interpret the intercept, you can interpret the slope. How do we interpret the intercept? Let's say you got an intercept of 24.45. How do we interpret that? Anybody recalls? Hello? Anybody recalls how to interpret the intercept of the model?
Professor, can I try?
Yeah, please.
If income increases by $1.
Intercept, yes.
Oh.
You guys are, yeah. Intercept, how do you, Hello?
Professor, when x is 0, then the intercept is showing the value for expected y?
Yeah, average y. Average y on average is 24.45 when x
Yes,
is
Professor.
0.
0.
How do you interpret the slope?
When we add 0.51 x1, we will get 1 y1.
Say it again. Say it again.
Average will get 1
No, please, from the beginning.
y1.
No, I cannot hear you. Sorry, your internet is not.
By adding 0.51, by adding 0.5, can you hear me?
By adding, what do you mean by, how do you interpret slope of a line?
Professor, can I try?
Yeah, please.
If x increased by one unit,
Yes.
then y on average increased by 0.51 unit.
Exactly. Is it, are you guys confused about intercept and slope of a straight line?
No, Professor.
I don't know. What happens? What have you learned from the calculus class? I don't know. Anyway, so this is how you interpret intercept and the slope. So this is what we did. We know how to calculate beta 2 hat, how to calculate beta 1 hat, and so on. And more importantly, how to interpret the intercept of an estimated line, how to interpret the slope of an estimated line. All right. So that is one part. Actually, honestly, for all other disciplines in the social science, their journey stops here. They say, oh, okay, we got the line. We have drawn the line. We know what intercept is, what slope is. We know the relationship between x and y. We know that if x increases, y on average increases by 0.51, and so on. So what else do you need? But for us, really, a new journey starts from here. Do you have any question about this brief overview of the econometric basic model? Any questions? Hello? Do you all
No,
know
Professor.
how to interpret intercept and slope of a straight line? I'll have to be very clear about that. Anybody got any issues with the intercept and slope of a straight line? How we interpret, at least how we get a slope, how we get intercept, how if an equation is given, how to draw a straight line. Anybody got any issues with that? Hello?
No, Professor.
You are sure? Because,
Yes.
yeah, because you need that.
And it's easy, but in the
Hello?
like some difficulty.
You have difficulty with straight line
Not here, like in the exam.
in the exam?
When I'm in the class, I can understand, but in the exam time, I like find some difficulty. Even if I know all the process, still I like.
Yeah, that is lack of, yeah, I don't know. That is maybe
I
lack of
don't
confidence.
understand the question. Like maybe it's my problem. I don't understand exactly, but I know how to solve, but I can't.
That you have to do a lot of practice to do that. Anyway, so let's move on to the new one. Now the next thing, after you estimate beta 1 hat, beta 2 hat, the next thing they do is something called goodness of fit. But we already know part of it. Goodness of fit, also called coefficient of determination. Goodness of fit, that means how much the line fits the data, how much the independent variable is explaining the dependent variable. Okay, so if independent variable X can explain independent variable a lot, then it's a very good fit. If independent variable can explain very little part of dependent variable Y, then the fit is actually bad, not so good. So there is a measure for that, how the independent variable is explaining the dependent variable. And that is called a goodness of fit, denoted by R square. Denoted by what? Denoted by big R square. Big R square. Goodness of fit or coefficient of determination, also denoted by R square. How do they do it? Here. So we are going to do this goodness of fit, R squared. Now, look at this line. So you have Y here, X there, okay? X on the horizontal, Y on the vertical. Look at this line. What is this line? This line is the regression estimated line. Y hat equals beta 1 hat plus beta 2 hat X. This is the estimated line. You have estimated beta 1 hat. You have estimated beta 2 hat. And you have drawn this line. Like our example, Y hat equals 25 point something plus 0.51 X. That kind of line is drawn here. Okay. If I ask you to draw a Y bar, you know what Y bar is? Hello? Y bar?
Yes, Professor.
What is Y bar?
The mean.
What type of mean? Remember, there are two types of means.
Conditional.
Conditional. Is it population mean or sample mean?
Population.
Population, no. Population mean is always denoted by expected value. Y bar,
Sample.
bar is always a sample mean. When you say Y bar, X bar, they are basically sample mean. You add all the values, divide by sample size, that there you get sample mean. Didn't you do the math, the calculation where you get X bar and Y bar?
Yes, Professor.
So this same thing, y bar is the sample mean. So let's say you have a sample of 30. So 30 values of y. How did you get y bar? Hello? How do you get the y bar? You add all
Add
30
all values
values,
and divide the sample.
divide by
sample.
30. That's how you get y bar. How do you get x bar?
Add all the value of x and divide it by 30.
30 is the sample size. Yeah, that is your sample mean of x, x bar. Y bar is the sample mean of y. I think I have told you like at least 50 times that sample mean and population mean are not same. Population mean means expected value, considering all possible values of the variable. Sample mean is just whatever sample size you have. If you have sample size 30, you add all the y values, divide by 30, you get the. Even there are maybe millions of y values, possible values, but you have taken a sample only of 30. That is a sample mean. Two very different things. If you
Yes,
don't,
Professor, it's clear.
hello?
It's clear.
Yeah, I know. I mean, I'm telling you many times. I have to tell you many more times. They are so very different. If you don't see the difference between population mean and sample mean, the whole exercise of econometrics or statistics is futile, is really futile. So anyways, y bar is a sample mean here. You have x values here, all y values here, and you get a sample mean. So if you want to draw that sample mean, what type of line do you expect? Hello? So x here,
A horizontal line.
yeah, it has to be a horizontal line. This line, this is a horizontal line. This is the sample mean you have from your sample. That is a number. So whatever the x values are, sample mean is same for your sample. So that is a horizontal line. Now you have drawn this estimated line. Okay, like here x increases, y hat also increases. So you have this estimated line. Remember, not population regression line. This is the estimated line. Now think about it. Y bar is this value, okay? X increases, y hat also increases. So you have this estimated line. Think about a point here. Can you see that point here at this? Can you see a
Yes,
point there?
Professor. Yeah.
Okay. That point is a point from the data. So when x has a value, y has also a corresponding value. Remember, if you recall your homework, you have x values and y values, corresponding x and y values. Even we did in the class, also in the exam, we gave one example, also in homework. So if you have x value, you have y value. If you have sample size 30, how many points like this will you get here on this space?
30.
30 points. Each point has an x value and a y value. All right. So here we picked one point from that 30 points. 1 point from that 30 points. What is this height then?
Y hat plus
no,
u.
forget about y hat. This point here. From here to this point, what is the distance? Excuse me. What is that height? That is y, actual y value from the sample, okay? So if x is xi, y is yi. So maybe if x is 100, maybe y is 80. That kind of values, okay? There are many other values like that. When x is 80, what is the value of y? When x is 120, what is the value of y? So all the values of x corresponding y's are here. We picked one value where x equals xi or maybe 100, y equals yi, maybe 80, something like that. So this height is y. What is this height up to this?
Y bar.
Y bar, exactly. If so, the height up to y bar is obviously y bar. So yi minus y bar. I can find the bar.
I can't hear you. It's noising.
Please, you guys, mute yourself. So y minus y bar. Think about it. Here is a y value. Here is this y bar. There are many other values of y corresponding to x. So it's a huge lot of values here, 30 values. Now, this distance, y minus y bar, is called the variation of y. Variation of y from its mean. Total variation of y from its mean. So the difference between y value and mean of y is called the total variation. Okay. Then what is this height? Up to this point, from the horizontal axis to up to this point, what is that height? Anybody?
Y
Please,
hat.
that is y hat. So y hat minus y bar, here y bar, y hat minus y bar y hat minus y bar is this distance. Okay, y hat minus y bar is this distance. This is, so the variation of y, meaning the difference between the actual y and the mean of y, is this whole distance. Okay, y minus y bar. Now our regression line, the estimated line, is halfway through here. So this distance, y hat minus y bar, is called explained variation. Explained variation. What does it mean? Somebody, please, you mute yourself. Could you? Hello, please mute yourself. So if you have question, you can ask, or else you mute yourself, and let us explain what this. So they are saying, what they're saying is, obviously any y value is deviated from its mean. So that deviation yi minus y bar is the so-called total variation of y from its mean. Now that total variation, that difference between yi and y bar, the whole thing cannot be explained by the regression. Regression line, estimated line, can explain only this much, y hat minus y bar. This much is explained by x. Why is deviating from y bar? Because x is increasing. As x is increasing, y is also increasing. So the variation of y is coming from the change in x. However, our estimated line can capture only this much, y hat minus y bar. That's why that is called so-called explained variation. The variation of y that can be explained by our estimated line. Then what is this? Y minus y hat. Y minus y hat.
But Professor,
Yes.
if x decrease, then what happened with y hat and y bar?
Say it again.
If x decrease,
Yeah.
then what will happen with y bar and y hat?
Y bar will remain the same, but then y value will go down. Okay.
Yeah.
If x increases, y increases. X decreases, y decreases. Yeah, true. But there is also a variation. That variation can be positive, can be negative. Yeah. So the variation of y is happening because x is changing. Okay. Now the question is, how much of the variation of y can be explained by x? That means can be explained by this regression line. We saw that only this much is, if x is xi, the regression line will tell you y hat is only this much. So this,
so when x decrease, y decrease, and the regression line will be changed.
No. It's the same relationship you are saying. X increases, y increases. X decreases, y decreases. That is the same line.
What about the line?
Which one?
The regression line.
See, that's why I asked you, do you understand the straight line? The regression line remains the same as long as intercept and slope remains the same.
Okay, got it. Yes.
The line you draw from intercept and slope. Is that clear?
Yes, Professor.
Okay. So here, from y to y hat, here, this part is not explained. This is also called unexplained variation. This is called unexplained variation. I don't know what happened here. So this is the unexplained variation. So now again, look at this point again. We are explaining only one point, but remember there are 30 points like that. One point here, yi. This is y bar. Yi minus y bar is the total variation of y from its sample mean. Now that total variation cannot be explained. Only one part of that can be explained by this line or by x. Which part? Y hat minus y bar. Y hat minus y bar is explained variation. Now y minus y hat is the unexplained, not explained part of the variation. Okay, so they have other names as well. Why they are giving other names? Let me explain. So now, if you have 30 values of x, you have 30 values of y. Then how many variations like this you can get? How many total variations you will get? Let's talk about total variation. You will get 30 total variation. If you get total variation, 30 total variations, some of them will be positive, like y is above the mean, sample mean. Some of them will be below the sample mean. So that will be negative. What do you do to get rid of negative? What do we do in statistics to get rid of negative signs? Hello? We do same old technique. You square them. You square them. If you square all the total variations, you will get rid of negative signs and you add them. Okay, that is called basically total variation or total sum of squares. Total sum of squares. So basically you are adding all the deviations from sample mean. If you have a sample size of 30, you have 30 deviations from sample mean. You square them, you add them. That is so-called total variation or total sum of squares. Remember, sum of squares. You get the deviation, this deviation, yi minus y bar. Square it. There are other yi minus y bars. Square them. Square all of them. Add them. So you are saying total sum of squares, TSS, also called SST or TSS. So that is basically a deviation like this, square them, add them. So that is actually, that is a technically speaking, that is a total variation or total sum of squares. Now, you also have explained variation. How many explained variations will you get? Again, 30 explained variations. You add them, you square them, you add them, you get the explained sum of squares, ESS or SSE. SS or ESS or SSE. Okay, that is ESS or SSE. What is that? Y hat minus y bar. Y hat minus y bar whole square summation. You square these all the deviations. You square them. You square them. You add them. You add them here. Summation. So there are 30 explained variations. You square all of them, you add them, you get the explained sum of squares. Then you have this kind of unexplained part, y minus y hat. You have 30 of them. You square all of them, you add them, you get so-called unexplained variation, also called residual sum of square, residual sum of ESS or SSE, sorry, ERSS, here ESS. So, skip this ESS part because that is going on. So once again, you have 30 data points because your sample size is 30. Then you have 30 points like this, X and Y, and you have estimated this line with the OLS formulas. Now you want to see the variation of Y. How much of this is explained by my regression line? How do you do that? You pick a point and you see that that point is Y minus Y bar. That is the so-called deviation from mean. And you square all the deviations, add them. That is called total variation of Y. Also called total sum of squares, TSS or SST, which is Y minus Y bar whole squared and summation. Summation goes from 1 to n. N is your sample size. Total variation or total sum of squares. Then this total of sum of square has got two parts. One part is explained part. Explained means explained by the regression line or explained by the independent variable X. What is that? Y hat minus Y bar. And you have 30 of them. You square all of them, you add them here. Y hat minus Y bar. You square them, you add all of them, you get explained sum of square or explained variation. That is one. Another one is beyond our regression line, not explained, also called a residual. It's like a residual. It's like a mistake. You could not explain that part of the variation. Which part? Y minus Y hat. Y minus Y hat. And you have 30 of them. You square all of them, Y minus Y hat. You square them. You add all of them. That is residual sum of squares or RSS. I hope you already saw this thing. Y minus Y hat whole squared. What is Y minus Y hat? Hello? Do you remember Y minus Y hat?
It was U hat.
It was U hat, exactly, residual. So this part is residual sum of squares. And this part is explained sum of squares. Total is TSS, total sum of squares. So let's see if you have any questions. So you have three things here. Total is called total sum of squares. Depending on your sample size, you will have 30, 40, 50. This Y minus Y bar, you square them, you add all of them. That is one part. Another part is Y hat minus Y bar. You square them, you add them. That is explained sum of square, also called explained variation. Another part is our old friend, residual sum of squares. Residual means Y minus Y hat. Y minus Y hat. You square all the residuals, you add all of them together, you get residual sum of square, RSS or SSI. Is that okay now? Question? Hello? Do you have any questions?
No, Professor.
All right. In that case, then, what is R square? What is the goodness of it? Goodness of it is now simple. It's a explained variation or explained sum of square what fraction of the variation of y is explained by x? Now we know this is the explained part. Explained sum of a square. This is the total part. So explained part divided by total part is the fraction of the variation of y explained by x. So r square is ESS divided by TSS. R square is ESS by TSS. Okay. So TSS equals RSS plus ESS. And R square is ESS by TSS. Explained sum of square divided by total sum of square. Very important statistic. Any regression analysis you do, second thing you report is R square. Okay. Now we know what R square is. R square is basically a ratio of explained variation and total variation. Explained part divided by total. ESS divided by TSS is the R square. So ESS by TSS, can it be more than 1? Is it possible to be more than 1? ESS by TSS? No way, because ESS is a part of TSS. So R square values lie between 0 and 1. If R square is close to 1, that means the fit is very good. If R square is close to 0, the fit is very bad. So R square lies between 0 and 1. For example, how you explain R square? Let's say R square is 0.9. How do you explain this number? 0.9. Remember, R square lies between 0 and 1 because in the numerator you have explained variation, in the denominator you have total variation. So the ratio has to be less than 1. Let's say you get 0.9. It's a very good fit. What is it telling you? This is what it's telling you. Remember this for the rest of your life. R square 0.9 means 90% of the variation of y is explained by x or by the regression. R square 0.9 means 90% of the variation of y is explained by x or by the regression. Is that clear? Hello? Hello?
Yes, Professor. Professor,
So
if it is exactly 1,
one is a very rare case. If you get R square 1, you say, immediately you should be suspicious. Something went wrong. That means you are saying residual is 0. There might be something big mistake you have made somewhere. But anyways, R square 0.9, 0.8, 0.7, 0.75, 0.95, 0.98. These are very good numbers. Okay. How do you explain? You see, for us, later on, explanation, interpretation of these things will be more important than how you derive them, okay? Because software will derive them for us. So you have to explain, but you know what is the theoretical background behind this. So if R square is, let's say, R square equals 0.78. How do you explain that?
Professor, can I try?
Yeah.
R square 0.78 means the variation in y is explained by x.
No. Anybody else? Hello? Anybody else? Okay, once again, let me go back to R square 0.9. R square 0.9, the interpretation is 90% of the variation of y is explained by x or by the regression.
Professor, then it will be 78% of variation in y is explained by x.
Yeah. 78% of the variation of y is explained by x or by the regression line.
Yeah.
Is it good? Yeah, 78% is pretty good, but depends on what model you have. If you get like 22%, R squared 22, how do you explain that?
It's bad.
How do you explain that? First thing.
R square 0.22 means the 22% of variation in y, which is explained by x.
Yeah. So you know that only 22% can be explained. The rest, 78%, unexplained. So that's not a good thing. That means your regression, there is something wrong with your regression line, regression model. Okay.
So we can say it is good if it is like over 50%.
Yeah, depending on your model. If it's a cross section, is okay. If it's a time series, maybe not. Depending on your model. But for us, we have to remember that the R square lies between 0 and 1. Closer to 0 is a bad thing. Closer to 1 is a good thing. Yeah. And a specific value of R square, we should be able to explain clearly without any confusion. R square 0.9 means 90% of the variation in y is explained by x or by the regression line. Okay. R square, any question? So once you estimate the intercept and the slope, estimate the line, draw the line, second thing in order is what? R square. You find R square and you explain R square. Everybody, you write a paper, everybody will look at your R square. Okay, they know if R square is 0.22, they will say, oh, okay, not a good job. All right. These are all practical things now. If you do any research, you work at any research organization or anything anybody doing economics, development or finance or anything, they will ask for this kind of statistics. Beta 1 head, beta 2 head, estimated line, fitted line, and then goodness of fit, R square. Do you have any questions? Can I move on now in that case?
Yes, Professor.
Okay. Then we will move on to other things. Really other things, important stuff we would like to move. A little bit of theoretical background and I would say I'll use this.
Professor?
Yes.
You explained like when R squared equal to 0 only if the SE equal to 0, which means that delta 1 hat equal to 0 and delta 0 hat equal to y.
Beta 0 is, beta 2 is?
I mean the property of R squared, the last one. Can you explain?
Yeah, what is your question?
Could you explain the property of R squared, the last one, the last line?
Professor, beta 1 hat equals 0 and beta 0 hat equal y bar, these things, I think.
Beta 1 hat is 0?
Yeah, the last line of the
Last line of the property of R squared.
Which line?
Professor, there is given like
Professor, the
beta.
properties of R squared, the last line.
Yeah, R
Properties
squared.
of R.
Yeah, so R squared lies between 0 and 1. That's what you're saying?
No,
Last
No,
line,
last one.
Professor.
The properties of R squared, the last one, R squared is equal to 0 only if SSE is equal to 0, which implies that what does it mean by beta cap is equal to 0 and beta.
Oh, okay, okay. So it's coming from the formulas, okay? So beta, here beta 1 is basically beta 2, okay? Beta 2. So beta 2, 0 means what? Beta 2, 0 means what? What is beta 2?
slope.
The slope. If the slope is 0, that means what? X increases y? If the slope of a line is 0, what type of line you will expect? If the slope of a line is 0, what type of straight line you will see?
Horizontal line.
Horizontal line. That is exactly this y bar, okay? No?
Yeah.
So is there any variation in y due to x?
No.
So x increases, y does not change. That means x is not explaining y at all. You see what I mean? So that means explain sum of square is just 0. X cannot explain because x increases, y does not change. That means x is not explaining y at all. Then explain sum of square is 0. The line is exactly like this y bar. The regression line, you will not see a line upward sloping or downward sloping. You will see a line horizontal. Okay. You think about it. Then what is beta 1 hat? If you have this line, y hat equals beta 1 plus beta 2 hat x. If beta 2 hat is 0, then what is y bar? What is the y hat?
It's beta 1.
Exactly. Y hat would be beta 1 and y bar will be also beta 1, and this part is not explaining. X is not explaining anything. That is the crucial point. When you get a 0, which is very unlikely, to be honest. If you get a 0, you will check your estimation method. Something is wrong. You might get very close to 0. But if you get a 0, that's technically speaking, beta x is not explaining anything at all. All right. Okay. Any other questions? Do you have any other questions?
No, Professor.
All right. So basically, for us, what is important is if you run a regression, for sure you will get a R square value. Very unlikely that you will get 0 or you will get 1, which are extreme cases. There must be some mistake you made. That's why you are getting 0 or 1, but you will get something in between, and you should have a sense of R squared. What type of R square is a good one? If it's a 0.9, obviously it's good. If it's 0.8, still good. 7 is okay. But if you get a 0.2 or 0.1, 0.05, 0.2, 0.23. These are poor numbers, and we know how to explain R square. Very important, how to explain R square. Okay, let's move on to the other kind of issues now. The next thing we should have is, the next thing we ask is, how good are the estimators? How good are the estimators? So what are the estimators? Estimators are here. Estimators, here is the estimated line. Beta 1 and beta 2 are the estimators. Let me write them first and then I'll ask the question. Beta 1 hat is an estimator of beta 1. And beta 2 Okay, so come to this point. Beta 1 hat is an estimator of beta 1. Beta 2 hat is an estimator of beta 2. Estimator, like, is it a constant or a variable? Let's say, let's focus on beta 2's hat. We will focus on this one from now on. Okay, you can do beta 1 hat. Our focus will be beta 2 hat, because this, the slope is more important than the intercept. So we focus on beta 2 hat, but you can do beta 1 hat as well. Beta 2 hat is an estimator of beta 2. Is beta 2 hat a constant or a variable? Hello?
Constant.
Is a constant. Okay. Any other thoughts? Anybody else? Hello? Anybody else got any other ideas? Do you remember X bar and mu? In the exam, I think we gave something like that. Do you remember? So let's say, forget about this econometrics analysis. I spent so much time on the statistic review. He said if X is a random variable, X is a random variable with mean mu. How do you write mu here? Let me see if I can get a mu here. Yeah, I will get a mu here. So if X is a random variable with mean mu and variance sigma square, what type of mean mu is? Hello? Can you hear me? Can you hear me?
Yes,
Yes,
Professor.
Professor.
So if I say X is a random variable, not related to regression analysis, just from statistical review. If X is a random variable with mean mu, what type of mean is that? Huh?
Population mean?
Population mean, exactly. And variance sigma square. And variance sigma square. What type of variance is that? What type of variance is that? Population or sample?
Population.
Population. Population. And then you get a sample and you sample of, let's say, size 30, and you find the mean of that sample. What do you call it? Let's say you collect a random sample and you a random sample of size 30 or n. Then if you get a sample mean from that sample, what do you call it?
Sample mean.
Sample mean. Sample mean, we denote that as X bar. Now, what is this X bar? Is it a constant or a variable?
Constant.
Is it a constant or a variable? X bar. How do you calculate X bar? How many X bar can you get from a population with mean mu and variance sigma square? How many X bars can you get?
30.
How many X bar can you get? No idea? One from one sample. And from if somebody else collects another sample, then what will happen? What will happen then? If 30 people go and 30 different samples are collected, then what happens?
30 X bar will get.
So what is X bar? Is it a constant or a?
It's a variable.
It's a variable. Did we talk about this? I also gave one in the midterm. This question number 2. So again, I actually cannot emphasize more on this thing. Sample statistic, like sample mean, these are not a constant. This is what? This is a random variable. If X is a random variable with mean, mu, and variance, sigma square, then there is something called sampling distribution of mean, which is saying sample mean is also a random variable with a probability distribution. X is a random variable, X bar is also a random variable. If X is normally distributed, X bar is also normally distributed. If we don't know the distribution of X, can we find the distribution of X bar? What will be the distribution of X bar? You guys forgot everything about statistical review. Sample mean. So once again, last time I'm reminding you, and I will not talk about it anymore. X is a random variable with mean, mu, and variance sigma. Then collect a sample size of whatever size n. Sample mean X bar is also a random variable with mean. What is the mean? Huh? What is the mean of X bar? Mu. And variance? Who can tell the variance?
Sigma square.
Who says who? Okay. Anybody else? Any statistician in this class, which we have talked about several times, and in my script I gave it to you. If X is a random variable with mean, mu, variance, sigma square, X bar is also a random variable with mean, mu, and variance. What? Anybody recalls anything? Sigma square is a close answer. Hello. Huh?
Sigma squared divided by n.
Sigma square? Yeah, go ahead. Sigma square?
Divided by n.
Divided by n. Exactly. Haven't we talked about this? Huh? Have we talked about this? Okay, even if you don't recall. So if X is a random variable, its mean, mu, and variance sigma square. X bar is also a random variable with mean, mu, and variance sigma square by n. More importantly, what is X bar? X bar is an estimator of mu. X bar is an estimator of what? Our focus is here always. Remember, estimator. Because population is not known. Then what we do is we collect sample and we find sample statistic like X bar. And then we say, oh, okay, but now we can talk about mu. Even though nobody knows mu, but we have X bar, and with X bar, we can talk about mu. Why? Because X bar is an estimator of mu. Guess what? What is an estimator of variance? What can be an estimator of variance? What can be an estimator of sigma square? Hello? Can you guess if there is an estimator of sigma square? Okay.
Sigma square by n.
No, actually, it's sample variance. Yeah, it's something similar. The sampling variance will be an estimator of sigma square, but it's close to sigma square by n. Sometimes they write it is sigma square is not known. Remember, this sigma square is not known. Is it known?
No.
So how can you use that as an estimator? Can you use an unknown thing to give an idea about another unknown thing? You have to use a known thing to talk about an unknown thing. That is the whole point of statistics. So when you don't know mu, you use X bar. You don't know sigma square, what do you use? What is sigma square? What is sigma square?
Variance.
What kind of variance? Population variance. You have to be clear, it's a population variance, it's not known. What can you do then? You can use sampling variance as an estimator of population variance. Remember this always. For us as economists, where you are using statistics, our focus is estimator. Population parameters are not known. So we resort to sample. And then we use sample statistics like X bar, like a sampling variance. Anybody recall the sampling variance formula? Do you know sampling variance formula for this X blah? Okay, you go and you look at it. I'll ask in the next class, sampling variance. I'll ask in the next class. Anyways, so the focus here is estimator. This X bar, sample statistic, sample mean. You are using it to talk about mu, population mean. Now, X bar is a constant or a variable? Clearly, X bar is a random variable and with a mean, with a variance. Similar thing here. So it's a digression here, okay? From here to there, we spend like more than 1 month to make sense of what we are going to do. But anyways, it's a digression.
Professor, I cannot hear you.
You cannot hear me? Why? Because some people are not muting themselves. So this is a digression. Okay, now let's get back to our beta 2 hat. Is an estimator of beta 2. So what is a beta 2 hat? Is it a random variable or a constant? What do you think? What do you think about beta 2 hat?
It's a variant.
It's a what?
Professor,
yes.
The variance, like the sample mean you wrote here, X bar is an estimator of mean.
Yeah.
For sigma square, like is it for variance of Y bar equal sigma square by N?
No. Forget about regression. Here, this is just probability statistics here. We are saying if X is a random variable with mean, mu, variance, sigma square, X bar, which is an estimator of mu, has also a probability distribution. It is also a random variable with a mean and variance sigma square by N. Now, what is your question?
No, Professor, no question.
It's nothing to do with regression. It's just a probability statistics kind of just review, refreshing your memories. I gave a question also in the exam. Anyway, so if beta 2 hat is an estimator of beta 2, then beta 2 hat is also a random variable. Beta 2 hat is also a random variable. Now, if that is a random variable, then our fundamental question is, can it represent beta 2? Beta 2 hat is an estimator of beta 2. The question is, what type of estimator? Is it a good, quote unquote? Is it a bad estimator? That kind of questions we have to ask. Whether beta 2 hat is a good representative of beta 2 or is a bad representative of beta 2. We hope beta 2 hat will be a good one. Now, there are some criteria for a good estimator. If I ask whether X bar is a good estimator of mu or not, what will your answer be? Huh? If X bar is a good estimator of mu or not?
Professor, how can you know, like without any calculation?
How do you know? Yeah, there are some criteria for a good estimator. There are some criteria for a good estimator, and we will discuss those criteria later on as we go. Okay, so for us now, we want to make sure beta 2 hat is a good estimator of beta 2. Good, quote unquote. And what do you mean by good? We'll discuss later. Now, to be a good estimator, beta 2 hat, to be a good estimator of beta 2, we need some assumptions. We need some assumptions for OLS. OLS, remember OLS? Estimators, ordinary least square estimators, to be good, quote unquote. Good estimators. Estimators of what? Estimators of beta 2 hat. So beta 2 hat is an estimator of beta 2. Beta 1 hat is an estimator of beta 1. For them to be good estimators, the following assumptions need to be satisfied. Believe me, the rest of the econometrics are just examining those estimators, sorry, those assumptions. The rest of the econometrics, and I have done 4 econometrics courses in my life, 1 in master's, 3 in the PhD level. The rest of the econometrics is really trying to check whether the assumptions are satisfied or not. Okay, so what are the assumptions? There are many assumptions. I'll pick only the major ones. Assumption number 1. So why are we doing these assumptions? We are doing these assumptions so that OLS estimators like beta 2 hat is a good estimator of beta 2. 1, the model, the econometric model is correctly specified. So what is the first assumption? The assumption is that, what is the model, by the way? Here is the model, okay? Y I equals beta 1 plus beta 2xi plus ui. That is the model. So first assumption is saying this model is correctly specified. What does it mean? It means at least 3 things, maybe 4, I forgot. At least 3 things when they say the model is correctly specified. Number 1, the functional form is correct. Meaning that is A, and you have questions you ask here. I'll explain, try to explain. A, the functional form is right. HEHT. Implying the release Linear. The model is linear. Is the model linear here? Is it linear here? Hello? Is it linear?
Yes.
How do you know it's linear? Huh? How do you know it's linear? Huh? What is the power of y?
1.
What is the power of x?
1.
You obviously say random term. So is it linear? Huh? How do you know whether an equation is linear or not?
Professor, the beta 1 and beta 2 cannot be known.
Known. Yeah, we know that. Beta 1 and beta 2 are not known. That's not the issue. Whether this is linear or not. The model, one, whether it's linear or not.
Linear.
How do you know? Huh? How do
So
you?
there is no power.
Power
No
of
power.
what? No power means what?
Number. Like
Huh?
if it's not linear, that time we can see that x square or division.
Where?
Something like
Where?
this.
On what? Power of what?
Sir, like
On X
b
on Y.
that is that x square.
X
If
squared
is
or
not.
y squared. That kind of power? Huh?
Yes. Yes.
Okay,
So this is
I'll
also a straight line and a straight line.
is that?
Upward sloping.
Upward or
Is
downward
that
doesn't matter. I'm asking a simple question. Is it a linear equation here or not?
this is linear? But
Yes, professor, it is linear.
Huh? It's linear, okay? So then what does it mean? The functional form is right, implying the model is linear. Is actually saying this. Whether your model here, you are writing is a linear model, okay? You are assuming a linear model, and this is correct. You are not making any mistake when you are writing this model is actually linear in reality. It's actually linear. But linear means, now here is the confusion about econometrics. When they say linear, they mean linear in parameters, not linear in variables. What are the parameters here? Huh? What are the parameters in the model? Hello?
Beta 1 and beta 2.
Yeah. When they say linear, they actually mean linear in what? Parameters. So when they say the functional form is right and basically saying the model is linear, when you are assuming linear, they are trying to make sure the model is linear in parameters. And parameters means here, obviously this linear in variables, y and x, also linear in parameters. So this kind of model is good. You can estimate. If you get something like beta 1 plus beta 2 square xi, that is a nonlinear model. What did I say? So if you get a model like this, here I'll spend some time on the linearity. So let's say you got something like, let's say the model is like this. Is it linear?
No.
No,
No.
it's no more linear. It's a non-linear model. You cannot handle this kind of model. OLS cannot handle this kind of model. So this is not linear in parameters. Let me write it here. Non-linear in parameters. Okay. How about a model like this? Let's say how about a model like this? Is it linear?
No, Professor.
This is not linear. But for regression line, this is linear. Not this one. I'll erase this. Let's say you got y squared equals beta 1 plus beta 2 xi plus ey. Is it linear? It's not linear actually, but it's linear in parameters. This is okay. If you get a model like this is fine. How about this? How about this? Is it linear? What is the left hand side?
Ln.
Ln. Here is log of y equals beta 1 plus beta 2 x plus ey. Is it linear? No, it's not linear, but OLS doesn't care. It's linear in parameter. Is it linear in parameter? Yes. There's no power in beta 1, no power in beta 2. It's linear in parameters. And you will see this kind of model. Let me draw another model. How about this model? Read it for me.
Professor?
Yes.
Sorry to interrupt. Like, how long is this going to go on? Like, because some of us have class from 6:30.
Yeah. Our class ends at when?
Like
6:30, Professor.
Our class starts at ends at 6:30. Okay. We will go up to 6:25 and I will call it a day. So okay. I'll give you 25 minutes. All right. Is that fine?
Okay, yes, Professor.
Okay, okay. So when they say model is linear in parameters, they are overruling this kind of things. Okay. Beta 2 square or beta 1 to the power beta 2 or log of beta 1, this kind of thing. But you have log of y equals beta 1 plus beta 2 log of x plus u. This is nonlinear, we know. But for regression analysis, this model is okay. As long as the model is linear in parameter, then that's fine. The functional form, you have to be careful about functional form is right. And also, I'll instead of writing implying, I'll write the model is linear in parameter. So if you have a square x square, it's okay. If you have y square, it's fine. But if you have beta 2 square or beta 1 square or beta 1 to the power beta 2 or log of beta 2, then that thing is not doable. So if you look at your homework, you'll see that there are models like this. Log of y and x here, log of y, log of x there. Sometimes y here, log of x there. So you have to be careful. These models are linear in parameters. They are doable. Okay. So when they say model is correctly specified, one of the things that they mean is this. The model is, the functional form is right. And model is linear in parameter. And then Another one, I'll just say another one and I'll call it a day. B, the model is correctly specified means very important one. All important independent variables are included in the model. What does it mean? Let's say you are doing a demand function. Okay, let's say it's a demand function. Y is quantity demanded, X is price. So here is the model, price and quantity demanded. Do you think all important variables are included here? Huh? Hello? So once again, let's say is the quantity demanded and you have price on the right hand side. So price and quantity demand relationship you are showing here. Do you think all important variable that determines quantity demanded are included in this model? What else should be included? Very important model. Who did Intermicro with me a little bit ago? Huh? Anybody here from Intermicro?
Yes, Professor.
So demand depends on what?
Professor.
Price.
It's
Income.
Price and what else?
Yes.
Income.
Income. So if you write a model like this, ignoring income, have you included all important variables that determine quantity demanded?
No.
Huh? Did you ignore income? Do you think income is an important variable?
Yes.
Yes, Professor.
Exactly. So when you say model is correctly specified, you are saying that all important independent variables are included in the model. That means if you are doing a demand model, you have included not only price, plus you have included also what? Income of the consumer. What else do you think is important for a demand? Do you think any other variable is important for demand? From your Intermicro? How about price of a complementary good? Do you think that's important? And so on. Anyways, so that's coming from theory. So two things now we talked about. The econometric model, assumption number one, the model is correctly specified. That means two things. One, functional form is right. If actually it's linear, you write linear. If actually it's not linear, quadratic, you write quadratic and so on. But make sure it's always linear in parameters. If it's not linear in parameters, it's not doable. Another one, all important independent variables are included in the model, and we'll talk about the other ones in the next class. I call it a day today, and we'll come back on next class. Please try to find.
Professor,
yes.
Please share all the recordings with us for
yeah, we did. I did share the last one.
Professor Micro, you didn't.
Huh?
Micro, you didn't.
Micro, I did. I already asked the. You emailed the TA.
Okay, Professor.
Yeah.
Professor?
Yeah.
When are you going to share the quiz marks?
Oh, yeah. I'm working on that. I did Intermicro. I'm working on the econometrics.
Professor, what about the homework?
Homework, it takes time. It's a long
Professor,
one.
is it possible to skip this one?
Which one? No. Homework, I think you are almost ready to now do the homework. Yeah, I'll email you when
Not
it's
so far, Professor.
Huh?
Do it later.
And that's how you learn. It has to be
yeah.
hard.
Okay,
Yeah.
Professor, when is the submission date for the homework?
Yeah, I'll increase. I'll email you the submission date as well.
Okay.
Professor, let's do some classes and then.
I'll check the homework and I'll check how much we did here. and then
Yeah,
I'll
that will be
decide.
better.
All right, guys. Then let's call it a day for today. Let's end the class. Unless you have
Thank you,
anything.
Professor.
Yeah, goodbye. Good night.